Hello everyone, my name is Mithun. I work as a solution architect for TCS. Today I'll be taking you through our journey of leveraging grid gain to overcome multiple performance bottlenecks and achieve our SLA targets. To set up the context, or probably to set up the context, the use case we'll be discussing today is a critical part of a large scale banking application that serves over 2,000 clients across India. Now, the system required ultra fast processing speeds, but as explained earlier, we encountered several challenges along the way. So, in this entire PPT, I'll primarily be discussing what were those challenges, or probably I'll start off with what was the use case, what were the challenges we faced, and how we overcame each of these challenges. So, let's just move ahead to the next slide. Okay, so in this slide, I have just given a brief overview of what I'll be covering as a part of this presentation. Primarily, I'll start off with the architecture and the use case overview. I'll follow up with the technical challenges that we faced and how we leverage grid gain primarily to overcome those challenges and achieve our SLAs. I'll also touch base on the optimizations we implemented, and finally, the most important part, the results that we achieved. I'll wrap it up with the key takeaways and learnings from our experience. So let's get started. To summarize, I have just listed the TPS that we achieved right in the beginning. That's the baseline TPS. So this entire slide shows the journey that we went through. Right from the baseline TPS, we started off with 900 records per second, and we finally reached around 21,000 records per second. So this slide gives or probably summarizes the entire tuning experience. I have also listed down what were the tuning optimizations we did uh, for in each of these stages, right from the baseline where 900 was achieved. We followed it up with some SQL and index optimizations, which made us reach 2500, following up with configuration changes, memory sizing, key value processing, etc., etc. I'll get into the details of each of these points. I would like to highlight that reaching 21,000 TPS from 900 was a journey for us. We have spent lots of sleepless nights working on tuning this application and working through each of these stages to achieve this particular final TPS that we have achieved. In the next slide, probably I'll walk you through the specific challenges we face and the optimizations. Moving ahead. Okay. Now here I'll be explaining the high level architecture and the use case. Now, instead of discussing the entire application architecture, which would be quite complex given the multiple layers and the components involved, I'll focus primarily on the architecture relevant to this use case. A key point I would want to highlight is that this particular use case was the primary SLA requirement that we had to meet at any cost. Okay, we were working with a 6 node grid gain cluster in production, with each node having around 512 GB of RAM. However, for during this discussion, I'll be primarily discussing of the testing we had done in the UAT environment, which was a 2 node cluster with the 512 GB RAM per node. Okay, I'll jump to the use case. So the use case was a simple file upload scenario wherein clients will upload files which can be in the range of which can have records in the range of 1 million to 50 million. There will be this will be a zip file, and each of these zip files might contain around 10 to 15 smaller files which are to be processed. Once uploaded, we have our containerized platform which will perform initial validations, passing the records and pushing these records to Kafka once the initial validations have been passed. Now, from Kafka, these records were again passed into a rule engine wherein we did some field level validation, some mandatory checks, regular expression checks, dependency checks. And finally, the validated records were pushed to again to a Kafka topic. Now, from this is the point from where we started our grid gain processing. Now, just to highlight, I have not there is lots of tuning we did on the microservice layer, on the file upload layer, and even on the database layer. I'm talking about the big data layer, which is post grid gain. I have not included any of those tuning numbers or achievements as a part of this particular discussion. I'm sticking only to the grid gain aspect. Moving ahead. Okay. So once the records are again pushed to Kafka from the rule engine processing. From here, we start off with the activities we performed in grid gain. Now what happens is we have created three caches in grid gain. The first one is a set of caches. We call them initial caches. Now these caches are primarily used to just process the records we have received in Kafka and put them into these initial caches. So if I have 15 files that have been uploaded within one zip file, now for each of these 15 files, I'll have 15 separate caches that I have added. There is another set of caches, probably the most important ones, which we call the primary caches. Okay, now these are the caches which we persist. These are the caches which are a subset of the big data database. So primarily these are the caches we'll be using further on to do database validations in Gridgain. So in this step, what we do here is we populate the primary caches here, and later on we leverage these primary caches to do database validations. Finally, we have a final set of cache which is again in line with the initial caches. So if we have 15 initial caches, there will be 15 final caches. Now these caches are the last set of data which have passed all the validations and cross joins. These are the caches from which data will be moved to our big data database. So this is a simple file processing flow, right from the point wherein the files are uploaded to the point where we do some initial validations across the containerized layer, containerized platform, followed by some critical cross joins and DB validations, which we are doing in our gridgain layer, and finally moving the data to our big data database. Okay, fine. I'll be moving ahead to the next slide. Okay, so we divided our services. Now, as mentioned earlier, there were three caches that we have created, and there were four services that we have created as a part of processing data from each of these caches. Now, I missed one point earlier. The first thing that we do once the data comes into GridGain is that we do a duplicate check across all these caches. So if I have 15 files, then there will be a duplicate check which will be run across each of these files to remove all the duplicates records from each of these files. This duplicate check will be followed by a cross-file validation. Now this is one crucial step wherein we apply joins across each of these files and we populate the primary caches. We have a service 3 which we use for streaming data from Kafka to Ignite or GridGain. And finally, we have a tokenization cache wherein we for two specific files we have to do tokenization of records. Now, this tokenization of records is done using a third-party tool. So we use this service to do tokenization of these records or send the record to the third-party tool and get the tokenized records back and save it in Ignite. So I have mentioned this here in this particular point I'm highlighting, wherein from the initial cache, the data goes to the third party tool for tokenization. Okay. Now, coming back to our current slide, initially we faced some deployment challenges in GridGain as to where we deploy these services. Now, since the Kafka data streaming and the tokenization primarily were involved in pulling data from Kafka and sending it to third-party tools, and also from pulling data from Kafka and saving the data in GridGain, we had deployed these two services inside our containerized platform. While the service 1 and service 2, which were primarily focusing on only on the GridGain processing were deployed on the grid gain servers, which is outside our container platform. This led to connectivity issues and inconsistencies in the future, which I'll come to later on. Moving to the next slide. Okay. So our here I've just listed down the SLA. So our SLA was overall our SLA was to process around 500 million records within a time span of 4 hours in production, which translated to 30,000 records per second. Now, since we were testing in UAT, our goal to achieve an end-to-end TPS was scaled down to around 10,000 records per second in UAT. Now, this 10,000 records per second is the overall end-to-end TPS that I am referring to. Right from the point the file was uploaded to the point all the processing is completed in the containerized platform, in GridGain, in the database platform, and the error file is generated, and the response comes back to the front end saying that the file is getting processed. The overall end-to-end TPS was expected to be 10,000 records per second in UAT. From the grid gain perspective, since each of these activities were happening one after the other, we had to achieve around 70,000 records per second in TPS so that the overall TPS uh, uh, with all other components comes up to 30,000 records per second. And again, as I mentioned earlier, since UAT is the platform we were using at this point of time, this was scaled down to around 24,000 records per second. This is what we had to achieve. Uh, Going ahead, again, we started off with uh, SQL joins as the primary mode of doing cross joins across files. But uh, the reason being, initially the file size was limited to around 50 MB or 40,000 records. But due to a consistent requirement, due to a requirement change, the file size increased exfold, exponentially rather, to directly to 50 million records per file. So 50 million being the max number, the total zip file size can range anywhere between 10 million to 50 million. But you can imagine our plight. Our entire architecture was based on the assumption that the file size would hardly be 50 MB to 50 MB, around 40,000 to 50,000 records. But now uh, catering to a file size which can be around 30 GB to 40 GB with 50 million records was something which we were not prepared for initially. Um, Also, the third-party tool that I referred to earlier, wherein we were using it for tokenization, had a limitation of around 200 records per second. So we had to this created a significant bottleneck, which impacted the overall TPS. Now, the we had we had to design a workaround to ensure that this particular bottleneck does not impact the end-to-end performance of our application. Now, what these challenges meant was that our initial approach was not going to scale, and we need to redesign a few components. Okay, when we started off testing, we were at one point we were in a stage wherein we used to upload a file and wait for hours for the file to get processed. We have seen scenarios wherein the file was uploaded at 6 o'clock in the night, and at 9 o'clock in the morning when we are coming, the file is still getting processed. We just wanted to see whether large files are getting processed end to end or no. Something that uh, we we have gone through these phases. Okay, so some files which should have been processed in 30 minutes were taking around 10 hours or so. That's how it happened when it started off. Now let's move to the challenges. So let's move to the next phase, wherein I've just given the or summarized the overview of our tuning approach. Now we started off. Now this is our tuning journey. I would just like to mention that this tuning journey that I have listed here is primarily based on our experience. We don't recommend or we don't ask anyone to follow us. This is wholly and solely what we saw as a part of the tuning exercise that we did. So we started off with SQL and index tuning, wherein we optimized the SQL queries and indexes. We followed it with some configuration tuning, in primarily the on the grid gain affinity key or partition or replication of cache, etc. We did key value processing. Now this is something which is very important from the TPS standpoint. We followed it up with some persistence enablement, which was also required, and finally the workaround to manage the third party tool dependencies. Now, each of these phases contributed to a slow increment in TPS, bringing us from the initial baseline TPS of 900 to the 21,000 TPS that we have achieved. Uh, in the upcoming slides, we'll do a deep dive into each of these tuning steps, discussing the changes we implemented and the results we achieved. So, starting off with the first step, the SQL and index optimization. Now, we had, as I mentioned earlier, we had three primary caches and we had set them to replicated mode. The reason being that we didn't want, since we were using SQL to apply joins, we didn't want any cross network joins to hamper the performance. That's the reason why we had planned that these three primary caches against which joins are going to be applied are going to be in a replicated format. This was the initial plan. But as I mentioned, we started with a very bad TPS of 900. So we started looking into explain plans and the indexes that were being used. We, based on the explain plans, we changed the SQL join queries that we had written earlier. We also added new indexes. We checked what indexes were being used and based on the sequence of field names in the index creation, and we changed those sequences also. We reached a point wherein whatever changes we had implemented in terms of tuning the queries and indexes were being applicable. Now at this point we saw a slight surge in the TPS. The TPS levels came up to around 2500 records per second in grid. In some cases, we also saw the TPS spike to around 20,000, but this was happening primarily if the number of records in the file was less. Now, if I upload a 10 MB file, the performance was much faster than if I am uploading a 1 GB file which consists of 1 million records, 10 million records also. Okay. While this was a good initial gain, we still had a long way to go in terms of achieving our SLA. So we moved on to the next tuning. The next step was configuration changes. Now here, the first major change that we did is we converted all the caches from replicated to partitions, and we changed our focus to the affinity key settings. So here we optimize the affinity keys and we ensure that related records were stored together so that the joins don't have to be cross network joins. One interesting challenge we encountered was determining whether all records from a zip file have been received in GridGain from Kafka. So basically, once the record once the file was passed in the Kafka layer, Kafka didn't have any idea, or the microservice layer didn't have any idea when the records from that file have all been sent to GridGain. So what we were doing here is we had an event lookup in place wherein uh, before processing, Kafka used to send the metadata of the file to GridGain, and then once Kafka starts processing, GridGain used to consistently compare or track the number of records received with the metadata, which had the total number of records. Now, for this, we had a lookup in place, which was being executed every 10 seconds. There was a lookup happening to measure the count between the total number of records which we received as a part of the metadata against the total number of records we have received in Kafka. Surprisingly, we found while we were analyzing performance, we figured out that this continuous 10-second lookup that we're doing was causing the threads to go into a wait state. And at some points, we even saw critical thread block errors, which was causing the server to go down. The reason being that since these queries were fired every 10 seconds, at some point of time, even these read queries were not getting loaded, since the write was also happening in parallel uh, from the Kafka side. So we did a small change. We just tweaked the 10 seconds to 2 minutes, or we increased the time span of these lookup events or lookup read events. Now this small change resulted in the TPS improvement of uh, from 2,500 to 4,000 records per second. Again, at times we were still seeing 20,000 TPS as earlier, but then that strictly depended on the number of records which were being processed in the file. Now, while this was a step forward, we still needed further optimizations to reach our target TPS, which led us to the next tuning step, the key value processing and the sizing optimization. Okay, so next we did the memory sizing exercise. Now here, initially we had started off with around two backups. We reduced the backups to now to one, because what we realized is, out of the three set of caches, the initial cache, the primary cache, and the final cache, the only cache that we are going to persist was the primary cache. The remaining two caches were cleared off or purged once the file processing was finished. So what we did is we uploaded some large files. We analyzed the amount of space these each of these records were consuming in our RAM and within our disk. We had enabled persistence just to check the memory sizing only at this point of time. Uh, we also analyzed the on heap and off heap memory allocation for each of these services, and we made some tuning. We tuned these on heap sizes, off heap sizes, etc., etc. We also realized that if we don't control the file processing from the grid gain size, is we could lead to RAM exhaustion, which would affect performance. Now, what this meant was, whatever files were uploaded from the client side, instead of giving the entire control to microservice, we decided to take control or lead the control from the grid gain side. So we redesigned it in a way that every file upload done by the client, the microservice will send the metadata to grid gain, and grid gain will check the current number of files it is processing, the amount of RAM available, and based on the availability, it will design a priority queue which will help us figure what file to process. So GridGain had complete control over the over what file to process when, and this control will gave us further flexibility in terms of achieving better performance with whatever RAM we had available. Because there is a possibility that 400 clients are uploading files all together. While the SLA strictly said that the start time would be right from the time the file is picked for processing, not the time the client uploads the file, which helped us tweak do this come up with this small tweak wherein GridGain was taking control, and it was not picking up the file till the point it was in a position to process the file. Now, with these changes, our TPS change improved to around 6,000 records per second, and which is again independent of the file size. We were still seeing issues, but 6,000 was still a better number as compared to 9,000. Moving ahead to the next step. Now, this was a game changer for us. I'll come to the reason why we started off with SQL probably later on, but here what we did here is we finally decided to move away from SQL, since the file size was increasing, and as the number of records that we had to persist in the primary cache was increasing, the joins were started taking more and more time. So we moved away from SQL and we came to key value processing approach using binary format. So here we tweaked our services which were using duplicate check and join functionalities, and they were rewritten, uh, which allowed faster lookups and reduced the query overhead completely. We also leveraged the Ignite compute tasks functionality for distributed computing, which was an excellent move, which improved our performance uh, tenfold, I believe. Okay, this change had a massive impact on TPS, and we saw our TPS increase to around 34,000. Now, this 34,000 TPS, the best part was this, even under heavier loads, we were consistently seeing 30,000 to 34,000 TPS, making our system more scalable and resilient to variations in the data size, which we were not seeing earlier. So basically, by eliminating SQL and moving to key value lookups, we unlocked the true potential of memory in memory processing. Probably this was a game changer for us. Uh, Moving to the next slide. Then we started focusing on the environment stabilization. Now here, as I mentioned earlier, I had four services, out of which two of the services we had deployed within the containerized environment, the connector, which was pulling data from Kafka, and the tokenizer. We realized that there were frequent disconnections happening mm, between these this service and the Ignite server, which was outside the containerized environment. So which was impacting our continuity. So in order to address this, we finally came up with a solution. Now we tried multiple things. We even tried moving the Ignite server within the containerized environment, and but finally we reached this conclusion that in our setup, in our case, the best suited infrastructure would be all processing done on Ignite, including the services, be outside the containerized platform. So we moved all the services outside the containerized platform within the Ignite server instances. That reduced the network errors drastically, and since disconnections was reduced, our TPS went up. Okay, correspondingly, we were also seeing some strip pool starvation errors, primarily due to port range conflicts. Now, this happened because there was like four services running on each of the two Ignite server instances, and these services were all using the same port ranges. It was for TCP and communication ports. So we changed these port ranges, and post these changes, we significantly reduced the network issues and the thread pool starvation issues, which resulted in a consistent throughput of 40,000 records per second. Now, this was probably the best throughput we have seen in our UAT environment. The next step was to enable persistence. Now, all this while I have continuously mentioned that we had to persist data in our primary cache, we were not persisting because we wanted to see how much we can scale without persistence being enabled. While persistence was uh, one of the primary requirements, because we stood a significant risk of losing all the primary cache data since we were not persisting it. So we enabled persistence, and we saw a drastic dip in the TPS. Now, when we started our analysis again, we realized that the SSDs which we were using for persisting the data had a slow disk IO. We analyzed the disk IO, and we then procured faster SSDs to improvise on the write speeds. In order to support this, we also made some changes to the write ahead logs settings and the checkpointing frequency with which we were writing to these logs. Now, with these changes, we were able to stabilize the performance. Hence, it it came down to around 25,000, but we were okay to handle 25,000. While this was lower than a 40,000 TPS, but we still achieved a critical benefit of fault tolerance, ensuring that no data would ever be lost in case of any failure. That was a necessary trade off, as data consistency and durability were just as important as the raw performance in our setup. Next, finally, the third party tool optimization. So, here, uh, as I mentioned earlier, the third party tool had a bottleneck of around 2000 transactions or records per second. And out of those 15 files, there were only two files which required this kind of tokenization. So what we came up with a service which we were leveraging to save the hashed key of the raw data against the tokenized values in grid game. So basically, once the raw data is passed into a third party tool, the data gets tokenized, you are saving the hashed value of the raw data and the tokenized value within grid game. So what this meant was that for whenever these two files are getting uploaded, we don't have to go to the third party tool unless the data is not available within grid game. And then this improved our performance drastically. Our end-to-end performance, which was limited to, which had the severe limitation of 200 records per second, which had the similar limitation of 200 records per second, we overcame it, and finally our TPS improved, uh, came um, uh, came to around 21,000 records per second, which was uh, very good as compared to where we started from. Though it reduced from 25K to 21K, it was still in line with our expectations. Since the overall TPS we were able to achieve was above 10,000 records per second. Now, with this, we had addressed all the major bottlenecks and optimized the system to improve our performance targets. Now, moving to the next slide, here we have just I would say this is a wrap up of our tuning journey. This slide summarizes all the key changes we implemented and the corresponding TPS improvements we achieved in each of these stages. Okay, right from the baseline TPS of 900 to the final TPS of 21K that we achieved post tokenization, and all the stages in between, the sequel to key value shift, the memory caching that we did, the persistence enablement, the stabilization and deployment adjustments that we did in the connector and the network issue that we addressed. Now, through these multiple iterations and targeted optimizations, we were finally uh, at uh, at a highly efficient and fault tolerant level with improvised performance. Next, I'll just summarize the key takeaways. Now, again, I'm repeating this. These key takeaways are strictly based on our experience in our setup for our project. Okay, so what we thought is sequel tuning alone was not enough for us. While we did our bit in improving the SQL queries, moving to key value processing and compute task was essential to scale the TPS. Partitioning and affinity key are extremely crucial, and proper partitioning strategies and affinity configurations minimized these cross-node communications, which again improved our performance drastically. Also, the memory sizing and caching strategies, the on heap, off heap configurations or allocations that we had done, it significantly improved the cache utilization with, and it also reduced the excessive GC that was being called. Finally, the deployment strategies in order to reduce the network optimizations and the infrastructure issues, deploying the thick clients within the server rather than the clients being within the containerized environments and the server being outside. This reduced significant network bottlenecks and connection issues, was uh, which was important in scaling the performance. And lastly, the enablement of persistence and the SSD upgrades that we did with the VAL tuning also helped us achieve our overall performance. Overall, the success of this project came from a holistic approach, which included all these points that I have mentioned as a part of the fine tuning configurations. And lastly, at present, we are operating at a grid gain TPS of 21,000 records per second. Um, Most importantly, overall, the end-to-end TPS we are seeing is around 13,000 records per second uh, with a two-node cluster. So we are yet to move to our production environment. We will be starting the production testing soon. But this, again, as I mentioned, all these numbers are significantly uh, good, and these are in line with our expectations from with which we started off with this particular tuning journey. Now, with respect to future plans, we have some more ideas wherein we want to apply these joins dynamically. So basically, we whatever cross joins we are doing in a static way at this point of time, we would want to make it dynamic. This is something which we are working on at this point of time. Probably we'll come up with a solution for that too, and if I get a chance to present next time on this dynamic joining success, I will definitely do it. But then, yeah, again, we'll have to go through this journey because we have just started on this particular activity. Um, I think that's it from my side. I would like to just sum it up by saying that tuning isn't just about making queries run faster. It's more about transforming how we handle data at large scale. So if we have to do these small things to and to finally achieve if the bigger numbers, the finally see the bigger picture. So we were at last able to turn a slow and unreliable system which we started off with into a highly scalable high speed platform. But I would say this is just the beginning. We need to work further and improvise it further for upcoming requirements. And that's it from my side. It was a pleasure presenting at this summit. And I'm looking forward to any questions, feedback, and suggestions from you all. Thank you very much.